and welcome for our discussions. Energy powers everything around us, from the smallest motions to the grandest innovations. It fuels our homes, industries, and aspirations. In this, we'll explore the incredible world of energy, its types, energy transfer, stored energy, and understand heat transfer. Let's dive in and spark new ideas and illuminate the path forward together. Welcome to the world of energy and energy transfer. Energy is the ability to cause change in an object. It can also be defined as the capacity of a system to exert or provide force for a certain interval. The change can involve either the motion or the position of an object or its particles. There are many types of energy, and according to Helminstein 2024, the following are considered types of energy. The first one is mechanical energy. Is an energy that results from either the movement or location of an object. Mechanical energy is the sum of kinetic energy and potential energy. An example is an object possessing mechanical energy has both kinetic and potential energy, although the energy of the one of the forms may be equal to zero. A moving car has kinetic energy. If you move the car up a mountain, it has kinetic and potential energy. A book sitting on a table has potential energy too. The second one is kinetic energy, is the energy of a body's motion that ranges from zero to positive value. An example is a child swinging on a swing. No matter whether the swing is moving forward or backward, the value of kinetic energy is never negative. The third one is magnetic energy. It's a form of energy stored in a magnetic field, often associated with magnets and magnetic forces. It's a type of potential energy that can be converted into other forms, like kinetic energy or electrical energy. An example is a stored energy in a magnetic field of a car starter, an MRI machine, or even the Earth's magnetic field. The fourth one is electrical energy. It's an energy form associated with moving electric charges, like electrons. It's the ability of charged particles to do work or apply force. Examples include the movement of electrons in a wire, powering devices like toasters or cell phone chargers, and even natural phenomena like lightning. The fifth one is potential energy, is the energy of an object's position. For example, when a child swinging on the swing reaches the top of the arc, she has maximum potential energy. When she is closest to the ground, her potential energy is at its minimum. Another example is throwing a ball into the air. At the highest point, the potential energy is greatest. As the ball rises or falls, it is a combination of potential energy and kinetic energy. The sixth one is chemical energy that results from chemical reactions between atoms or molecules. There are different types of chemical energy, such as electrochemical energy. For example, a good example of chemical energy is an electrochemical cell or a battery. The seventh one is nuclear. It is an energy resulting from nuclear reactions or changes in the atomic nuclei. The example is nuclear fission, nuclear fusion, and nuclear decay are examples of nuclear energy. An atomic detonation or power from a nuclear plant are also examples of this energy. The next one is thermal energy, or heat energy that reflects the temperature difference between two systems. For example, a cup of hot coffee has thermal energy. Additionally, you produce heat and possess thermal energy in relations to your surroundings. There are two forms of energy. The macroscopic forms. These energy forms are related to motion and the influence of some external effects such as gravity, magnetism, electricity, and surface tensions. Examples include kinetic energy and potential energy. The second one is microscopic forms. These forms of energy are those related to the molecular structure of a system and the degree of the molecular activity. The sum of all these microscopic forms of energy is called the internal energy of a system. Internal energy, it is the microscopic energy due to molecular motion and interaction. The macroscopic potential energy and kinetic energy. The kinetic energy, this is the energy that a system possesses as a result of its motion relative to some reference frame. When all parts of a system move with the same velocity, the kinetic energy is expressed as capital letter K and E equals 1/2 multiplied by mass multiplied by velocity. The key E, or the capital letter K and E, stands for the kinetic energy in kilojoule. Letter M is for mass per kilogram. V is for velocity, which have a unit mass per second. Meter per second, rather. We have an example. A toy car with a mass of 0.5 kilogram is moving at a velocity of 4 meters per second. We have to calculate the kinetic energy in kilojoules. So we have the given mass, which is 0.5 kilogram, and the velocity of 4 meters per second. The thing we do is to write the formula. The capital letter K and E equals 1/2 multiplied by mass by volume. First thing we do is to substitute the values into the formula. So KE equals 1/2 multiplied by 0.5 kilogram, and then we multiplied it with the 4 meter per second velocity. First thing we do is to calculate the velocity. So 4 meter per second is cube, so it has a parenthesis. So 4 times 4 equals 16. So therefore it would be 16 meters squared per second squared. Next thing we do is to multiply the mass and the 1/2. So we multiply the 0.5 times 0.5 times 16 joule. So 0.5 times 0.5 equals 0.25 times 16 joule equals to 4 joule. Next thing we do is to convert the joules to kilojoules. So let's have this. 1 kilogram of joules is equal to 1000 joules. So 4 joules is divided into 1000 joules per kilogram. Kilojoules. Now let's move on to potential energy. This is the energy that a system possesses as a result of its elevation in a gravitational field. So PE is equals to mgh or mgz. So the PE is the potential energy in kilojoule, and letter M stands for mass, which have a unit of kilogram, and letter G is the gravitational acceleration, which is constant, which is the 9.81 meter per second squared on Earth. So Z or H is the height. So we have an example. A 2.5 kilogram book is placed on a shelf that is 1.8 meters above the ground. So we have to calculate the potential energy of the book in kilojoules relative to the ground. using the acceleration due to the gravity as 9.81 meter per second squared. We have the given, the mass, which is 2.5 kilogram, and the acceleration due to gravity, which is 9.81 meter per second squared, and the height, which is 9.8 meters. So first thing to do is we should write the formula first. So capital letter P and capital letter E equals mgh with small letter mgz, and then we substitute the values into the formula. So now we have PE equals 2.5 kilogram times 9.81 meter per second squared and 1.8 meter. Calculate the potential energy in joules. The PE would be 2.5 times 9.81 times 1.8 joules. So now the potential energy is 44.145 joules. And then we convert the joules to kilojoules, since we know that 1 kilojoules is equivalent to 1000 joules. So the PE is 44.145 joules divided by 1000 joules per kilojoules. So the answer now is 0.044145 kilojoules. So the potential energy of the book is approximately 0.044 kilojoules since it is being rounded off. Now let's move on to total energy of a system. So the total energy encompasses internal energy, which includes molecular kinetic and potential energy. So E is equals to capital letter U plus capital letter K and E plus PE is equals to U, and also consider the potential and kinetic energy formula. So E or capital letter E stands for total energy measured in kilojoules or kg. Capital letter U, also called the internal energy or the microscopic energy stored within a system. Ke is kinetic energy or the energy due to motion, and letter PE is potential energy, energy due to elevation in a gravitational field. Letter M for mass of the system per kg, and capital letter V for velocity with a unit of meter per second. Letter G, small letter G is gravitational acceleration, which is 9.81 meter per second squared on Earth. Z or H is the height above a reference point, which is have a unit of meter.
Good day everyone, I'm Aliaga Jasmine, and now let's proceed to stored energy and transient energy. Energy plays a vital role in every process from powering our homes to sustainable life. To understand energy more effectively, I will be explaining about these two fundamental types of energy, which are the stored energy or the potential energy and transient energy or the kinetic energy. So, what is stored energy? Stored energy is the energy that is accumulated or trapped in an object or system due to its position, condition, or configuration and is available to be released to perform work. It remains in the system until it is released, sometimes unexpectedly, which can cause hazards if not properly controlled. The examples include, first, mechanical stored energy. A compressed spring holds elastic potential energy that can be released suddenly when the spring expands. Second, gravitational stored energy. An object elevated above the ground, like a rock on a cliff, has gravitational potential energy due to its height. Next, hydraulic stored energy. Pressurized fluid in a hydraulic system stores energy that can move machinery when released. Next, pneumatic stored energy. Compressed air in a hose or tank stores energy that can power tools or equipment. Next, Chemical stored energy. Energy stored in chemical bands such as in fuel, batteries, or food which is released during chemical reactions. So here's the real world example. A cold spring in a machine stores mechanical energy. If released without control, it can cause injury or damage.
Now, let's move on to transient energy. Transient energy refers to a temporary, short duration burst or change in energy within a system, often caused by sudden changes or disturbances. It is not a steady state condition, but a brief event as the system moves from one state to another before settling. In electrical systems, transients are momentary bursts of energy characterized by a very high voltages and currents lasting from microseconds to milliseconds. This can be caused by lightning, strikes, switching operations, or internal equipment turning on and off. For example, electrical transient surges induced on power or communication lines due to lightning or switching devices. Another example is mechanical transient responses when a system changes suddenly from one steady state to another, such as variations after a shock or impact. To differentiate the stored energy and transient energy, here's the table. So, stored energy are the energy which remains within the system boundary as an inherent property of the system, while the transient energy are the energy which can cross the system boundary. An example of stored energy are the internal energy, potential energy, and kinetic energy, while transient energy are the heat and work. Stored energy can be defined for a state, while transient energy can be defined for a process. Stored energy are thermodynamic properties, while the transient energy are not thermodynamic properties. Stored energy are state function, while the transient energy are path functions. The stored energy are not boundary phenomenon, while the transient energy are boundary phenomenon. Stored energy are cyclic integral is zero, while in transient energy, the cyclic integral or integral is not zero. In stored energy have a unique value for each equilibrium state, while in transient energy do not have unique value for each equilibrium state.
Let's move on to energy transfer. There are two types of energy transfer, which are the heat transfer and work transfer. But I will only explain the heat transfer. But before that, what is energy transfer? Energy transfer is the process in which energy moves from one place, object, or system to another, often changing form in a process. It involves the relocation or transformation of energy without any loss or creation of energy. In accordance with the law of conservation of energy, which stated that energy cannot be created and destroyed but converted and transferred. Heat transfer. Heat transfer is the process in which the thermal energy moves from a region or object at a higher temperature to one at a lower temperature due to temperature difference. It involves the exchange of heat between physical systems and continues until thermal equilibrium is reached, meaning both systems attain the same temperature. This transfer of heat can occur through these three fundamental mechanisms. First is the conduction, convection, and the last one is radiation. Conduction is the direct transfer of heat through material or between materials in physical contact caused by microscopic collisions and variations of particles. Heat flows from the hotter region to the colder one through this particle interaction. For example, a metal spoon heating up in a hot soup
transfers heat by conduction. Next is convection, the transfer of heat by a both movement of fluids, the liquid and gases. Warmer, less dense fluid rises, while cooler, denser fluid sinks, creating currents that transfer heat. This can be natural due to buoyancy force or forced using pumps or fans. Boiling water circulating in a pot is a good example. And the last one is radiation, the transfer of heat through electromagnetic waves, primarily infrared radiation, which does not require a medium and can occur through a vacuum. The sun warming the earth is a prime example of heat transfer by radiation. So, heat transfer is the natural flow of thermal energy driven by temperature differences, occurring via conduction, convection, and radiation, until temperature equilibrium is achieved between interacting systems. In conclusion, understanding the different forms of energy transfer and concept of stored and transient energy is essential for analyzing how energy moves and changes within system. Stored energy represent potential energy held within objects or systems, ready to be released, while transient energy involves brief, dynamic bursts during changes or disturbances. Together, this concept help us manage energy safely and efficiently across various applications in science and engineering. And that would be all. Thank you.